This is an overview of the Chapter 12 problems that we'll be looking at in class. And I do want to thank you for the work you've been putting in. This is my 2025 spring class. Doing a great job. So I thought I'd just go ahead and put together just kind of an overview of the types of problems that you're going to face in Chapter 12. So let's imagine this is an Erlenmeyer flask, and we're going to have some sort of just solution, water, pure water, but we're going to make from this pure water either an acid or a base solution. And we're going to use weak acids and weak base solutions and want to know what their pH is after they're added. So let's say we have an acid, and we'll just represent it as H, the acidic proton, and A is the conjugate base, that when we put it into the water, we're going to get some sort of equilibrium between the A minus and the HA in the water. It's going to come to equilibrium because these are both weak. So it's kind of our weak acid, weak base problems that are just in water, not necessarily reacting with some other agent. It's just reaction of the weak acid with water, or we can have the base being put into the water and we're going to have some amount of the weak acid formed, because there's going to be an equilibrium. When you have a weak acid and a weak base combination, they're going to come to some equilibrium, and we understand those equilibriums in water as either Kb for the base or Ka for the acid. And what that means is just really it's the equilibrium of the weak acid with water. Reaction of HA with water makes H plus and A minus. Or if they give us a Kb, it's the salt form, so it's usually some sort of counter ion. And we don't really going to worry as we move on in these problems. We're not going to worry about the counter ion because it just stays as an ion, not affecting the reaction in the solution at all. Whether it be with a strong base, weak base, it doesn't matter. It's just a spectator. So from here on out, we'll just disregard it. But we can have then a salt added to water, and we have a given Kb value, wherein we'll have to figure out how much of the HA has formed as it comes to equilibrium. So we'll have some problems that kind of focus on just adding a weak acid or a weak base to water and wanting to know either one, how much of the other species you have, or the pH. The pH is often used to measure as a metric the acidity of water, which is really important for biological, activity or whatever. We often will look at the pH for these combinations. So that's one. The second one, it kind of deals with a strong. We'll go to the other side. We'll have a strong acid plus a strong base. So we'll have that kind of situation where we don't have a weak, acid with water. We'll have three things added together. We'll have the water, maybe as a solvent for one of these two, the strong acid, strong base, or both. And it's happening in the water, the reaction, but unlike over here where it's just reaction of these with water, one of them, acid or the A minus base. Here what we're going to do is have a reaction of these two with each other, and then as they react, we'll see which one's which one is left over in excess, because then we can just take the concentration of the excess and determine the pH, because it's really just going to be, these are so strong, when they go to their products, strong bases make hydroxide and strong acids make H plus, they don't come back. There's no equilibrium. There's no K values for strong acid or strong base. Why? Because they just completely go to the other side with whatever they're reacting with, whether it be water, or in this case, again, these types of problems, what we're going to look at is combining a strong acid and a strong base. So for example, we might say for a strong acid, let's use HCl, and let's use for the strong base the classic NaOH. Well, those are going to react not with the water, but in the water to make H2O, which we have a whole lot of, which we never track the molarity of. It's always around 55 or so in terms of its molarity, and it would make also plus sodium chloride. So it's not like we're worried about some equilibrium between products and reagents. It's just going to completely go to this down here. But what we will worry about is what if I have, and I'll just use some blocks to represent amounts. What if I have, in terms of moles, I have this much, and in this case, I have half as much to react with the HCl. Then what you would do is, after the reaction, you would have left over some of that HCl floating around in the water, which is going to completely dissociate to make H+. So it's usually just find how much of this you have left and work from that to determine the pH. If it's excess HCl, then you just find the molarity of it and take the negative log of it, and that's your pH. If it's NaOH that you have excess of, well, it's hydroxide, so we have to kind of use that equation. I'm going to put them in the middle, some of these common equations that you often use in chapter 12. You have one that's just hydroxide concentration times the H+ concentration is equal to 10 to the minus 14th. That's a common, I guess, equation you use to jump from concentration of one to the other. Or, as we've seen more in class, we can take the negative log of both sides, and if we do that, we can have the negative log is P, so we can say the POH, negative log, plus the pH+, this is concentrations we're looking at, is equal to 14. It's just a negative log of one side and a negative log of the other would give us this equation here. So using this equation here, we could find out if we had excess OH after these two come together, the strong acid and the strong base, and it wasn't excess acid, let's say it was more NaOH. You would take the negative log of the concentration, put it into this equation, move it to the other side, and when you subtract from 14, whatever you have is your negative log of OH, that would be your pH. All right. So again, these two equations you might use, and there's, let's do one last one. There's a type of problem that you'll have, and it's the kind of the hardest one, so I'm going to leave it for down here. And we've looked at it, in class a couple of times, and that's wherein you have a strong acid or strong base with the counterpart as a weak. So with, in this case, we would say if it's a strong acid, we'd say the weak base it can be combined with, or the weak acid. And again, it'd be a combination of these two. I'll put them in the black here, strong acid with weak base. I'll use a different color, green. Or we can consider a strong base with a weak acid. And we're always, for chapter 12, going to consider these reacting to endpoint or to equivalency, meaning we're going to have a reaction where we have an equal mole amount of the H+ and the OH that's generated. So let me go ahead and show you an example of this. Let's say we have a strong acid, or strong base, sorry. So we could use, for example, calcium hydroxide. Now, right out of the gate, we might want to just simplify here. Remember how we said if it's a ion like sodium and calcium's a 2+, we could just say, you know what, I'm going to just disregard, because that's never going to change. I'm just going to consider it as 2OH- that's generated. And really, I'm just going to say all I care about is knowing how much hydroxide I have. That'll help us, I think, simplify some things. It's a strong base we're considering in this particular case. We can have that react with a weak acid. I'm going to use acetic acid, but I'm just going to represent it as HA as our weak acid. We use that up here. And so we can say, I'll find out the mole amount of strong base that I have. I'll find out the mole amount of HA if it's possible to do that. And then what I'll do is have that completely react to give us the, at equivalency, we'd have complete reaction to water plus A minus. And if you do that, what you can do then is when you get to equivalency, you'll work through ice. But when you get to equivalency, we know that if it goes to endpoint, this will be 0. And this will be 0 because that's what endpoint means. We've taken it so the strong base has been, say titrated the weak acid to equivalence point or to endpoint. And we know then that the change, I'm just going to say minus X here, that whatever it is, we would have X amount of A over here. We would have an equivalency here that, or HA, we can say if I have XHA, I have XA minus because we had to subtract that amount to reach equivalency, and that gives us the exact amount over here. Okay, well, what's the big deal? Well, unlike up here, where if we had a strong acid, strong base at equivalence point, you'd have just a neutralized solution and it'd just be pH of 7 and everything would be hunky-dory. But when you have a weak acid titrated with a strong base and you sort of make the conjugate of that weak acid a weak base, it tends to equilibrate in solution in water. It won't stay just completely over on this side. So what we have to do is kind of two ice tables. One to kind of deal with the boom, as we've said in class, maybe deal with the boom. And the boom was the strong base. Deal with the boom. Make sure that gets neutralized. And we did that. But then after that, you have to set up a new ice table with that A minus. You have to say, A minus, you're still in solution with water. And you're going to come back to form a little bit of that HA plus hydroxide. You're going to do this in solution just because that's what happens when you have a weak acid and weak base. They're going to kind of come to some equilibrium. And they have K values. So we would take that initial amount of the, I'm going to just give it an arbitrary value. Let's say it came out to be 0.125 moles. I'm just coming up with an arbitrary value. Water, of course, we don't care about. We had just titrated completely to the right side, the HA, so it's gone. And we have 0 amount of hydroxide that we've formed from this reaction. So the change would be, if it's a K value, and it's usually going to have a small k, either be base or acid, the Ka is going to be usually very small for the, the Kb we're dealing with. The Kb and the Ka are usually small. So you're going to use the approximation. It's a small amount of X, and we make then plus X plus X. And so we can go right to law of mass action, where we say the Kb is going to be equal to, now I'm going to be careful, I'm going from moles to molarity. I'm going to take that 0.125, which minus that X is not going to have much of a change in its value, but I do need to divide by the volume. So the total volume, not TV, but total volume, you'll need to divide that mole amount by. And if you do this using a K value, B value that's given, you'll be able to solve for X, which represents the concentration of hydroxide. Once you have that, then it's kind of, you're rounding third and heading to home. You would take the negative log of that, plug it into here, subtract it from 14, and you would have the pH. We'll have some problems like this. I hope this gives you an outline of the 3 types. Kind of the easiest is just a weak acid added to water, or a weak base added to water. What's the pH? Strong acid, strong base, either to neutralization, or even if you have an excess, if it's to neutralization, the pH will just be 7, because again, these don't have K values. Don't have to worry about a law of mass action. You may have to worry about an ice table to figure out who's left, but we can just take the negative log of whoever's left and plug it into this equation. Or if it's acid like we had here, it's just the negative log is the pH. Then last, the hardest one, where we have 2 ice tables. And when are you going to have that? When you have a weak base with a strong acid, or a strong base with a weak acid. Those combine. I'm only going to consider these reactions to equivalence point, this last one, because it's just a little bit harder if we don't have equivalence point reached. Thanks. Bye-bye.